And these quantized electron energy levels, such as observed in the Frank Hertz experiment and proposed and used in an ad hoc fashion by Bohr in his atomic model, kind of suggests that electrons are a wave, forming standing waves inside the atom, thus giving you the specific spacing in the harmonics and whatnot. So why not, right? De Broglie said exactly that. By the way, his name is, I believe, according to a French person, pronounced De Broglie. Not De Broglie, not De Broglie, De Broglie. He was thinking, since light have wave properties and particle properties, as we've discussed earlier, this wave-particle duality, why can't this also work for all kinds of matters, including electrons? So to apply the wave-particle duality for matter, what he needed a wavelength, because we already have this expression. We already have E equals h nu. So we know what frequency we can talk about, but what's the wavelength? Because we don't even know anything about these waves, so we don't know about their phase velocity. We might know about, as a group, how fast it's moving. That's the group velocity, but not anything about the phase velocity in order to use V equals F lambda. So we need some other way to define lambda. So he looked at, okay, for a photon, what else do we know about the photon? Well, we know this energy is also through relativity, special relativity to be specific, E equals mc squared. Once you take out the rest mass, here m naught, it becomes this. And this applies, of course, for a photon, because a photon travels at the speed of light, which is, by definition, relativistic. And rest mass it has is 0. So, you can relate the energy to momentum. So, as a particle, of course, in that sense, a photon has momentum. You can actually observe this by shining a very intense focused laser beam at, say, like a very small mass, like a reflective sphere that's fairly small in light. It's been done. You can see it. It's pretty cool. So from this, we can actually, for the photon, we know the photon's speed, which is c. And so combining these things, we know that P is equal to h divided by lambda. And so lambda is related to the momentum of the photon, whereas the frequency, as I've said before, is related to the energy of the photon, both by Planck's constant. What if we apply this to matter as well? Because matter has energy, matter has momentum. We can equally work out the frequency and the wavelength for matters, and then maybe talk about them in terms of waves. Just to get a sense of these numbers, for an electron at different energy, so of course no energy and mass, we can work out the speed and the momentum as well, thus getting the wavelength. So if we have energy of 1 electron volt, meaning we take an electron, accelerate it through 1 volt, we get 12.3 angstrom. And of course an angstrom is equal to 10 to the minus 10 meter, useful unit for talking about atomic spaces and whatnot. When you get to 10 eV, wavelength continues to get shorter and shorter. And even at 1 eV, 12.3 angstrom, that's like the size of roughly 12 hydrogen atoms. It's not very big. So that's why in most cases we try and observe electron, the wavelength is so small we don't see it acting as a wave because the wavelength is small. What we will need then, in order to see these kind of wavelengths, by the way, these kind of wavelengths is similar to basically your X-ray wavelengths, so it passes through a lot of matters. Where it comes into play as a wave and you see interference is if you have crystal spacing, and it is precisely in these types of experiment where we can see these wave properties of the electron. And finally, it was done in 1927 by Davison and Germer. Once again, two experimentalists, two different people, and also by around the same time by Mr. Thomson as well. So Thomson did a transmission diffraction through a thin foil, and he saw diffraction rings, as we've talked about. And then Davison and Germer had crystalline planes forming more or less like a thin film interference, but more precisely it's diffraction gratings as well. And we'll look at the Davison-Germer experiment in more detail in our demo. And much later, in the 1960s, finally, we were able to also build double slits that are small enough for the electrons and observing the interference fringes from it. So with all these observations, it was pretty much undisputable that electrons also have wave behavior, and so proving the existence of matter waves. Now, what exactly are these waves of? In the sense that when we have sound waves, they were waves of pressure or longitudinal displacement. When you have EM waves, they are oscillation in electric field and magnetic fields. What are these matter waves of? Before that, I'd like to refer you to this next video, which shows you what happens in a electron diffraction experiment.